Really an incredible journey into one of the deepest mysteries in science, what reality is at its most fundamental level.
That's right.
And specifically, we're taking a deep dive into your fascinating hypothesis about the quantum wave function. The idea that it's an imperfect mathematical construct which only probabilistically reflects a deeper, infinitely complex reality of fluctuating energetic waves.
It's definitely a bold hypothesis, and, it plugs right into a century of really intense debate among physicists, philosophers, too.
So that's our mission today.
Exactly. Our mission is to unpack this idea, see where it fits in the landscape of quantum interpretations, and, well, see how it holds up against some really tough theoretical challenges.
And we've got a good set of sources to guide us.
We do. We've got sources laying out everything from, philosophical distinctions to some cutting-edge theorems, even historical attempts to model randomness. It's quite a spread.
Okay, so let's unpack that central question right away. What exactly is the wave function? I mean, is it a real thing, physically, or is it just, a tool, a way for us to understand something else?
That's the million-dollar question, isn't it?
Quantum mechanics, it's incredibly precise in its predictions,
Yeah.
right? Astonishingly so. But this central thing, the wave function, CI, its actual nature is still, well, hard to pin down.
It really is, and that slipperiness is right at the heart of the famous quantum measurement problem.
Right.
Which leads us straight to this fundamental split, this dichotomy. Is the wave function ontic or is it epistemic?
Okay, break that down. Ontac first.
Sure. So the ontic view, or ontic, basically says that CI, the wave function, corresponds directly to physical reality itself. It is the thing.
It is what's real.
Exactly. Interpretations like many worlds or de Broglie-Bohm theory, they really lean into this sontic perspective.
Okay, so if ontic means the wave function is reality, what's the other side of that coin? The epistemic view.
Right. The alternative is the epistemic view. And this perspective holds that F represents our knowledge or our information about a system.
So it's about what we know, not what is.
Precisely. It reflects our ignorance, you could say, about some underlying, more complete physical state. Physicists often label that deeper state lambda.
Okay, and this is where your idea comes in strong, isn't it?
It seems to fit right in.
Your hypothesis, this imperfect mathematical construct, that sounds firmly epistemic. The wave function isn't the reality itself.
But rather a reflection of it.
And the infinitely complex energetic waves you propose, that would be the deeper reality, the ontic state, the lambda.
That's exactly how it maps onto this framework. And what's,
Right.
well, appealing about an epistemic view at first glance anyway, is how neatly it seems to handle the collapse of the wave function.
The infamous collapse.
Right. In this view, it's not some weird physical process happening. It's just an update of our knowledge, like a weather forecast changing when you look out the window and see rain.
Okay, that sounds elegant, less mysterious.
It does seem elegant, but, and this is a big but, it assumes there is this underlying reality, this lambda, and describing that robustly comes with its own set of challenges, sometimes pretty significant ones, as we'll see.
And this whole debate on phatic versus epistemic, it's not new, right? Einstein was involved?
Oh, absolutely. This goes way back. Einstein himself really preferred a statistical interpretation. He saw the wave function as fundamentally an incomplete description of what's really going on.
So this really pushes the question. Is the randomness we see in quantum mechanics, the indeterminism, is that baked into reality itself?
Or is it just about what we don't know yet?
Right. Is it onphitic randomness or epistemic ignorance? Your hypothesis, taking that epistemic stance, well, it's signing up for a pretty demanding research program to answer that.
It definitely is.
Okay, so to really get a feel for your hypothesis, let's say the boldness and maybe the difficulties too, we need to see how it stacks up against the major players, the existing interpretations.
Time for the comparisons. Let's look at three big ones. First up, the Copenhagen interpretation, often called the orthodox view.
The standard one, sort of.
Sort of the default for a long time, yeah. It embraces indeterminism as intrinsic, fundamental. Probabilities are calculated using the Born rule, that's the recipe connecting psi to measurement outcomes.
And the wave function itself in Copenhagen.
Its status is ambiguous, often very instrumentalist. You know the phrase, shut up and calculate.
Heard it.
That often gets associated with Copenhagen. It treats the collapse during measurement as real, but doesn't really define it physically, What is a measurement?
That's the big problem there, the measurement problem.
Yeah.
What actually counts as a measurement to trigger this collapse?
Exactly. It's the key challenge. Now, Copenhagen resonates a bit with your skepticism about psi being fully real, but it doesn't give you that underlying mechanism for the probabilities that you're looking for.
Okay, so that's Copenhagen, kind of ambiguous. What about the other extreme? Many worlds? MWI.
MWI is, well, diametrically opposed to your starting hypothesis. It says psi, the wave function, is the fundamental complete reality, and crucially, it never collapses.
Never collapses. So what happens when you measure something?
The universe branches. It splits into parallel realities, one for each possible outcome.
Wow, okay.
So it's fully deterministic, actually, and local. The probabilities we experience are just emergent from our perspective within one branch. MWI is strongly fontic. It elevates the wave function to, like, ultimate reality.
Branching universes. That's a big pill to swallow.
It's a very different picture, for sure.
Okay. And the third major player, the Broglie-Bohm, the pilot wave theory.
Right. This one proposes a sort of dual reality. There's a real pilot wave, which is psi, the wave function, and there are actual particles with definite positions at all times.
So both are real.
Both are real. The wave guides the particles. There's no fundamental collapse needed. The probabilities we see just come from us not knowing the particle's exact starting positions. It's deterministic.
And the catch.
The main conceptual price is explicit non-locality. That spooky action at a distance Einstein disliked so much. It's built right into the theory.
So it shares your idea of an underlying reality, the particles, separate from size.
Yes, but crucially, the wave function itself, the pilot waves, is still considered a real physical thing. It's sonotic in that sense.
Okay, so we have this whole range. Copenhagen's ambiguity, MWI's I is everything, Bohm's psi guides real particles. Seeing these laid out, what really jumps out at you when you compare them to your initial idea?
Well, what jumps out immediately is a major hurdle. While your intuition has echoes in some of these, especially the idea of something deeper than size, there's a powerful theoretical result that really challenges the simple epistemic picture.
Ah, okay, this sounds serious.
It is. It's the Pusey-Barrett-Rudolph theorem, or PBR theorem. And it's not just philosophical hand-waving, it's hard math.
Right, our sources called it a hidden rigidity in the quantum formalism. Sounds like it puts some serious constraints on things.
It absolutely does. So the core idea of the epistemic view, remember, is that different quantum states, different sysosis, could actually represent overlapping knowledge about the true underlying state, lambda.
Okay, like my weather forecast could be 70% chance of rain and yours could be 80%, but we're both talking about the same underlying weather system.
Exactly. Your hypothesis, with an imperfect psi reflecting a deeper reality, is a perfect example of this kind of thinking. Classically, that makes total sense. My knowledge about one coin flip doesn't affect yours about another separate coin.
But PBR says.
PBR theorem shows that this classical intuition breaks down spectacularly in the quantum world.
Okay, let's unpack PBR. It shows a contradiction comes from three assumptions.
Right. Three assumptions that all seem pretty reasonable on their own. First is realism. The idea that there is some objective underlying physical state, lambda, that determines how measurements turn out.
That fits your infinitely complex energetic waves.
It does. Second assumption, epistemicism. The quantum state, psi, is just our knowledge about lambda, and different psi-simus can overlap in the possible lambdas they represent.
Which is the core of your hypothesis.
Exactly. And the third assumption, preparation independence. This is fundamental to how we do science. It just means if I prepare a quantum system over here and you prepare another one, totally separate, over there.
Their underlying states, their lambdas, are independent. My preparation doesn't magically influence yours.
Precisely. Seems obvious, right? But the PBR theorem proves, mathematically, that if you accept all three, realism, epistemicism, and preparation independence, you run into a direct contradiction with the predictions of quantum mechanics when you consider experiments on combined systems.
Wow. Okay, so you can't have all three.
You cannot. Something has to give. This forces a really stark choice, either. The quantum state must be ontic. It has to directly represent reality, meaning assumption 2, epistemicism, is false.
So psi is real in some direct sense.
That's one option. Or the other main option is that even apparently separate, non-entangled quantum systems have this deep non-local connection that violates preparation independence. Assumption 3 is false.
Meaning preparing my system does somehow instantly affect the possible states of your separate system. That sounds Radical.
It's extremely radical. So what does this mean for your hypothesis?
Yeah, what's the bottom line for the idea of an imperfect construct?
The bottom line is that your straightforward hypothesis, in its simplest form, hits a massive roadblock with PBR. It suggests that the connection between psi and reality is much, much tighter than the simple epistemic picture allows.
So I'm forced to choose.
Pretty much. You either have to abandon the purely epistemic view and accept psi as ontaic, directly real, which goes against your initial premise, or you reject preparation independence, which is a huge step with profound implications for locality and causality.
Or maybe challenge realism itself.
That's a third way out, yeah. Some interpretations like cubism do that, making psi purely subjective belief, but that moves away from your idea of objective energetic waves being the underlying reality.
So PBR essentially forces the wave function to be much more real than just knowledge, unless we accept some really strange non-locality.
That's a good way to put it. It really tightens the screws on purely epistemic models.
But still, that intuition about infinitely complex energetic waves, it feels like it should connect somewhere, right? Our sources mention quantum field theory, QFT. Does that help?
Ah, yes, QFT. This is where the energetic waves, part of your intuition, finds a really strong resonance. QFT is our most fundamental description of physics, and it represents a huge shift.
Oh, so.
It sees the universe not primarily as particles, but as continuous space-filling quantum fields, things like electrons, photons. They aren't the fundamental things. They're just localized excitations, like ripples or vibrations, in their corresponding fields, the electron field, the electromagnetic field.
Okay, so the fields are the underlying stuff.
Exactly. And that language maps incredibly well onto your energetic waves that compose matter.
It's like the field is the ocean, and the particles we see are just the waves on it.
That's a great analogy. And QFT also directly includes something like your randomized indeterministic fluctuations.
Really? Yeah.
Through vacuum fluctuations. Even empty space. The vacuum, the lowest energy state, isn't truly empty in QFT. It's described as a seething cauldron of activity.
Wow.
There are these temporary random fluctuations in energy, particles, and antiparticles popping into and out of existence constantly. And these aren't just mathematical artifacts, they have real measurable effects.
Like what?
Like the Casimir effect, two uncharged plates placed close together in a vacuum will actually be pushed together by these fluctuations. And the Lamb shift, a tiny change in the energy levels of atoms. These are real consequences of vacuum energy.
That's fascinating. So QFT seems to really back up the energetic waves and the fluctuations part of the hypothesis.
It definitely supports the ontology of waves and fluctuations being fundamental. However, and this is crucial in standard QFT, the basic equations that govern how these fields evolve, they are still fully deterministic and unitary, just like the basic Schrödinger equation.
Ah. So the fluctuations are part of the quantum description, but they don't explain the randomness of measurement outcomes.
Exactly. The randomness of vacuum fluctuations is a feature described by the probabilistic quantum state of the fields. It doesn't, by itself, solve the measurement problem or explain why we get this outcome instead of that one. Standard QFT still has that issue.
So my hypothesis, by suggesting these fluctuations are the source of the probabilities we see, is actually making a pretty significant leap beyond standard QFT.
It is. It's trying to use the ontology of QFT, the fields and fluctuations, to actually solve the measurement problem, which standard QFT doesn't do on its own.
Okay, now the idea in my hypothesis that quantum randomness comes from some underlying, maybe classical-like reality that has random fluctuations.
Yeah.
Has that specific path been tried before?
Oh, yes, extensively. And exploring why those attempts didn't quite pan out is really instructive. Two major research programs tried this: stochastic electrodynamics, or SED, and Nelson's stochastic mechanics.
Okay, tell me about SED first.
SED was a purely classical theory. It took classical electrodynamics and basically added a real classical random background field filling all of space, the zero-point field, or ZPF.
And the idea was?
The idea was that particles, like electrons, are constantly being jiggled or pushed around by this random classical field, and maybe that jiggling could explain quantum effects.
Did it work at all?
It had some surprising early successes. It could derive the Casimir effect classically, explain van der Waals forces, even reproduce the behavior of the quantum harmonic oscillator. It looked promising for a bit.
But. There's always a but.
A fatal but. SED fundamentally fails to correctly model the hydrogen atom. Electrons in the model tend to just absorb energy from the field and fly away from the proton they self-ionize.
So it can't explain why atoms are stable.
Exactly. It fails to explain the stability of matter, and it also completely fails to reproduce quantum interference patterns, like in the double slit experiment. It strongly suggests quantum reality isn't just classical physics plus some noise.
Okay, so SED didn't work out. What about the other one, Nelson's stochastic mechanics?
Nelson's approach was mathematically more sophisticated. He tried to derive the Schrödinger equation itself, starting from classical diffusion processes like Brownian motion, the random jiggling of pollen grains in water.
So, deriving quantum mechanics from classical randomness.
That was the goal. He postulated some kind of universal background stochastic process, a continuous random jiggle affecting every particle. And mathematically, it was quite remarkable he actually did derive the Schrödinger equation.
Wow. So that sounds like a success.
Mathematically, yes, but physically, it ran into huge problems. First, what is this universal jiggle? Its physical origin was completely unknown, just postulated.
Yeah. An unexplained jiggle.
And more seriously, it struggled profoundly with entanglement. Trying to reproduce the non-local correlations of entangled particles using only local diffusion processes proved exceptionally difficult, maybe impossible. Even Nelson himself later expressed strong reservations about whether it could be a viable physical theory.
So, both of these major attempts, trying to get quantum randomness from an underlying classical random process, they ultimately failed, especially when faced with things like stable atoms and entanglement.
That's right.
What's the big takeaway from those failures?
The really powerful lesson is that quantum reality seems to have a structure that's fundamentally different from classical reality, even classical reality with added randomness.
It's not just classical plus noise.
Exactly. Quantum mechanics, especially how it describes composite systems and entanglement, encodes correlations and relationships that you just can't seem to mimic by adding random fluctuations to a classical setup. Any hypothesis like yours needs a way to handle that unique quantum structure, particularly nonlinearity and entanglement, that goes beyond just assuming some simple background noise.
Okay, so if classical-style stochastic processes don't seem to be the answer, where does the idea of fundamental randomness fit into modern physics thinking?
Well, this brings us to a really important distinction we need to make involving environmental decoherence.
Decoherence, right, I've heard that term.
Decoherence is a standard, well-understood process within quantum mechanics. It's not a new theory, but part of the standard picture. It explains why we don't usually see weird quantum superpositions at the macroscopic level, like Schrödinger's cat being both alive and dead.
How does it do that?
Basically, any quantum system inevitably interacts with its surrounding environment. Air molecules, photons, whatever. These interactions rapidly entangle the system with the environment, effectively leaking the quantum coherence away.
So the environment kind of observes the system constantly.
In a sense, yes. This interaction quickly makes the system look classical to us. It explains why the possibilities seem to be distinct classical states. Cat alive or our cat dead, not a superposition.
Okay, so decoherence explains why the menu of options looks classical, but it doesn't actually pick which option happens, right? It doesn't solve the measurement problem itself.
Exactly, that's the crucial point. According to standard quantum mechanics plus decoherence, the whole combined system, cat, box, environment is still technically in one gigantic superposition. Decoherence explains the appearance of classicality, but not the selection of a single outcome.
Ah, okay, so there's still a gap.
There is, and that's where a different class of theories comes in, objective collapse theories.
Objective collapse.
Okay.
How are these different?
These theories propose a much more radical step. They fundamentally modify the Schrödinger equation itself. They're not just interpretations of the existing math, they change the math.
How do they change it?
They propose that wave function collapse is a real, physical, spontaneous process that happens randomly throughout the universe, completely independent of any observer or measurement.
Spontaneous collapse.
Yeah.
Happening all the time.
Yes. This aligns perfectly with your intuition about randomized indeterministic fluctuations being the objective source of probability. In these theories, the fluctuations cause the collapse.
Okay, that sounds much closer to the spirit of my hypothesis. Is there a main example of a theory like this?
The most well-known is probably the Ghirardi-Rimini-Weber theory, or GRW.
GRW. How does it work?
GRW basically says that every elementary particle in the universe has a tiny, tiny probability per unit time of spontaneously undergoing a localization, or a hit.
A random hit.
A random hit. This hit instantly collapses its wave function, localizing its position to within a certain small region. The proposed rate is incredibly low for a single particle, maybe one hit on average every 100 million years or so.
So for one electron, nothing much happens.
Right. For microscopic systems, these hits are so rare that standard quantum mechanics works perfectly well almost all the time. But consider a macroscopic object, like a cat or even a dust mote made of billions upon billions of particles, all entangled together.
Ah, so if one particle gets hit,
Because of entanglement, if just one constituent particle gets a spontaneous hit, the wave function of the entire macroscopic object collapses almost instantly.
and since there are so many particles,
With something like 123 particles in a macroscopic object, the collapse rate for the whole object gets amplified enormously. You end up with billions of collapses happening every second for any macroscopic thing.
so that forces macroscopic things to always have a definite position, a definite state.
Precisely. It solves the measurement problem in a very direct, observer-independent way. The collapse is just a fundamental physical process.
Okay, that sounds, well, like a solution. Does it have downsides? A price to pay?
It does come with costs. These theories have to introduce new fundamental constants of nature, the rate of the hits, the localization precision. They also technically violate energy conservation, though by such a tiny amount it would be incredibly hard to detect so far.
Mm.
And formulating a fully relativistic version that works seamlessly with spacetime has been a major ongoing challenge.
But here's something really interesting. Unlike Copenhagen or many worlds, these objective collapse theories, they're actually testable, right?
Yes. That's a huge point. Because they modify the fundamental dynamics, they make slightly different predictions from standard quantum mechanics under certain conditions.
Like what kind of predictions?
Things like a tiny amount of spontaneous heating in all matter due to the energy added by the collapses, or a loss of quantum interference patterns for surprisingly large molecules, larger than standard QM might predict, because the collapse process kicks in.
So experiments could potentially distinguish GRW from standard QM.
In principle, yes. There are active experiments trying to push the boundaries to look for these subtle effects. This provides a concrete scientific path for taking an intuition like yours and turning it into a falsifiable model.
Okay. This has been a real journey through quantum interpretations. Let's try to bring it all together now. If we give my original hypothesis a kind of report card, based on this deep dive, how does it fare?
All right, let's break it down. Your hypothesis really had three core claims. First, the ontological part. The idea of energetic waves as the fundamental reality.
How does that hold up?
That's actually the strongest aspect. The intuition that reality is made of fields or waves aligns remarkably well with quantum field theory, which, as we said, is our most successful fundamental framework. So, high marks for ontological plausibility there.
Okay, good start. What about the second claim? The nature of the wave function itself, the imperfect construct.
This is where the trouble starts. The claim that the wave function is just an epistemic tool representing incomplete knowledge that faces a really severe challenge, probably fatal in its simple form, from the PBR theorem.
Because PBR forces psi to be more directly tied to reality.
Exactly. The theoretical evidence strongly suggests that psi must have a direct ondectic connection to reality to avoid those radical consequences like violating preparation independence. So the purely epistemic part of the hypothesis struggles badly.
Okay. And the third claim, the mechanism for probability, the randomized fluctuations, causing the indeterminism.
This idea that quantum randomness comes from some underlying, perhaps classical-like stochastic process. Well, as we saw with SED and Nelson's work, that approach has historically been unsuccessful.
Because quantum behavior isn't just classical plus noise.
Precisely. Those models failed to reproduce key quantum features, especially entanglement. So simply adding random fluctuations to an underlying classical-like reality doesn't seem to capture the essence of quantum probability.
So it's a mixed report card. The waves idea resonates, but the imperfect construct idea for psi and the simple random fluctuations mechanism run into serious problems.
That's a fair summary. However, this doesn't mean the core intuitions are worthless. It suggests they need to be reconstructed into a more sophisticated, coherent physical model.
How would that reconstruction look?
Well, the most promising path forward seems to be keep the QFT-like ontology of field waves, but abandon the purely epistemic view of the wave function. Instead, embrace the idea that the fluctuations are real physical processes that actually change the quantum dynamics.
And that leads us where?
That leads directly into the framework of objective collapse theories, like GRW.
Okay. So a revised hypothesis, one that keeps the spirit but fits the physics better, might look like this. Let me try. Ontology. Reality is fundamentally quantum fields. The wave function, or wave functional for fields, is the real ontic state of these fields.
Yes, optic.
Dynamics. The evolution isn't just the smooth Schrodinger equation, it's fundamentally indeterministic. There's a modified equation that includes a real, physical, random process, those fluctuations, that causes spontaneous collapse, like in GRW.
Exactly. The randomness is part of the fundamental law.
And emergence. Because macroscopic objects collapse extremely rapidly, combined with decoherence smoothing things out, we get the stable, classical-looking world we experience.
That's an excellent reconstruction. It takes the core intuitions, waves, fluctuations, randomness, and builds them into a coherent, modern physical framework that directly addresses the measurement problem.
And this reconstructed model is causal, but not deterministic.
Precisely. It's a prime example of how quantum mechanics has forced us to separate causality, events having causes, from determinism, the future being fixed by the present. Objective collapse is causal. The collapse events are physical causes, but fundamentally indeterministic or stochastic.
So connecting this back to the big picture, the ultimate nature of reality, whether it's deterministic like many worlds or Bohm, or fundamentally random like objective collapse,
Yeah.
that question is still wide open.
It remains one of the biggest open questions in all of science. Your hypothesis, once refined and reconstructed along these lines, points directly towards one of the leading testable contenders in that grand debate.
And the final answer won't just come from philosophical argument.
But from experiments. Future experiments probing the subtle differences predicted by these competing views of reality will hopefully be the final arbiter.
It's really fascinating how a simple-seeming intuitive idea can launch us into exploring the absolute cutting edge of physics and philosophy. You ask a question that cuts right to the core: what is reality made of? And is the future truly open, or is it already written?
And that leaves a really profound question for you to think about. If quantum mechanics is fundamentally indeterministic at its heart, as your initial intuition suggested, and as theories like objective collapse propose, what does that really imply? What does it mean for big ideas like free will? Or even just for how predictable the universe can possibly be? It opens up a huge landscape for further thought.
A vast landscape indeed. Thank you for joining us on this deep dive. We hope you feel a little more informed, maybe a bit challenged, and perhaps even more curious about those energetic waves that might just be composing everything around you, including yourself.